EXØ-1 is a high-performance, hyper-versatile, multi-segment water rocket. It's designed to push the limits with conventional PET plastic pressure chambers and carry avionics packages and experimental payloads to altitude. It's also designed to fly as reliably and as conveniently as possible. In this video, we'll look at the design of the rocket, how it's built, and how it performs in practice. We start off with a bunch of plastic bottles, 5 to be precise. As a water rocket, EXØ-1 needs to be big in order to reach the performance goals we want, so we have to turn these 5 bottles into one long pressure chamber. There are several ways you could do this. You could use Robinson couplers, or you could take the bottle rings and form one long cylinder. But the way that EXØ-1 achieves this is with a technique called splicing. A normal plastic bottle has a nozzle at one end and a closed base at the other. In order to connect several of these bottles together, we need to have nozzles at both ends. The way we do this is pretty simple. We cut the 2 bottles in half, shrink the end of one down using hot water, sand again, wipe down, sand again, wipe down again, and then finally apply a high-strength construction adhesive to the end of each bottle. For most of my rockets, I use PL Premium, which you can find pretty easily at most hardware stores. Once the glue has been applied to the inside of the outer bottle and the outside of the inner bottle, the two get pushed together until there's just about an inch of overlap on the seams. And now we wait. The package says that the glue cures in about 24 hours, but this is way too short, and if you pressure test after only a day, you're almost guaranteed to have leaks. I let my splices sit for about a week before I do initial low pressure testing on them. Once the splice has passed testing to 20 psi to verify that there are no huge leaks, we have to wait another week before performing the full pressure test to 120 psi. This test is done outside with the splice filled all the way up with water and then also tied down to a board. This might seem like overkill for a water rocket, but yeah, it's better to be safe than sorry. This process gets repeated a second time depending on the block version of the booster we're building. Speaking of which, let's just run through what the main versions of EXØ-1 are. EXØ-1 has flown in 4 different configurations over its lifetime. It's more like 10, but whatever. Block 1, 2, 3, and 3+. The block numbers correspond directly to the number of pressure segments that make up the pressure chamber, so block 1 is 1 bottle, block 2 is a splice and a bottle, and so on. And a plus is added onto the end of that if the chambers are expanded. So for example, Booster 2 in its current configuration is a Block 3 vehicle, with each segment making up 1.5 liters of volume, whereas Booster 3 is a Block 3 Plus, with each segment making up over 2.5 liters of volume. The block numbers determine the performance and therefore the capabilities of each booster. Alright, it looks like our splices have cured and passed testing, so now let's get on to the booster construction and integration process. After both splices have dried and been qualification tested, they're screwed together with tornado tube couplers on the nozzles. These couplers are designed to create vortices as you swirl water around inside, so they make water transfer between segments very easy. As a bonus, they also hold high pressures well. Most of the time. Don't worry about that. Anyways, once the splices have been connected, a third bottle is added on top to form a Block 3 EXØ-1 booster. This booster is pressure tested to ensure that there are no leaks in the couplers, and then it's ready for full integration. Each EXØ-1 rocket can be separated into 3 main categories: pressure, aerodynamics, and recovery. We just finished talking about pressure, so let's move on to aerodynamics. This category is made up of the parts that are necessary not only for the rocket to fly high and fast, but also for it to remain stable and structurally sound in flight. The first thing added to the pressure chamber is the airframe. This is a little different than conventional solid rocket airframes. The airframe on EXØ-1 is made out of sheets of heavy-duty cardstock that are wrapped around the pressure chambers. They don't need to be extremely strong. The pressure chamber provides most of the strength, but they do need to be rigid enough to prevent bending moments in flight. A slight bend at 150 kilometers an hour could lead to a complete structural failure of the vehicle, which is something you generally want to avoid. Once the airframe has been attached, it's time for fins. EXØ-1's fins are made up of rigid cardboard or foam core board, which is wrapped in duct tape for waterproofing and additional strength. This is probably a good time for me to address the tape situation. Yes, there's a lot of duct tape on this rocket, but none of it's actually used to hold anything down. Everything is glued beforehand, and the tape is really only a backup measure to ensure that if the glue does debond, pieces won't start flying off in midair. You might see a lot of this tape specifically around the nozzle and midsection as well. This is actually reinforcement for the pressure chambers. Even just some duct tape around them is enough to raise the maximum pressure of these chambers by about 10 psi. So yes, I see how this looks, but all of it does actually have a good reason for being there. Anyways, after being taped, the fins are attached to the pressure chamber with hot glue. Yeah, don't hate on hot glue. I've launched rockets that went so fast the fins ripped off, but the actual glue stayed intact. If it's stupid and it works, it's not stupid, okay? The fins get 2 wooden dowels, each attached to them for support on landing and to keep them aligned as the pressure chamber expands when it's filled with air. Once all 4 fins are on and aligned, we're basically done with aerodynamics and we can get on to recovery. EXØ-1 has used several different recovery systems over the past 2.5 years. Booster 1 used a god-awful fall-away nose cone design that originally flew on Phoenix, and it flew on the one flight that Booster 1 flew. But Booster 2 has used several versions of different recovery systems. It's used the variations of the version 2 system, but by far the most reliable and effective recovery system that I've built is version 3. I have a whole video on this from 2024, but the V3 recovery system essentially consists of an ejection spring to push the parachute out, a door to cover the chute and keep it packed ahead of launch, and a carefully timed motor that releases an elastic band when simulations predict the rocket will reach apogee. The motor electronics are as simple as possible to ensure maximum reliability. There's a 9-volt battery in the nose cone, a switch to arm the system, and a separate launch detection switch that completes the circuit when a pin is pulled out on liftoff. The motor rotates at about 15 RPM, and when it gets nearly parallel to the rubber band slips off and the spring ejects the parachute out the side of the recovery bay. After about 35 flights of this system, I have only ever had one recovery failure that was a direct result of an issue with the system itself. By now, we're just about done. We have a fully assembled booster, we have a pressure chamber, an airframe, fins, a recovery system. All that's really left is to add a nose cone, which is pretty simple. It's just a cone made out of cardstock. It's made out of cardstock to make sure that it can crumple to dissipate the kinetic energy of an impact in case a rocket doesn't deploy the parachute. We then add the parachute shock cord, launch lugs, a few labels, and now we have a fully completed EXØ-1 booster that's ready for launch. Of course, in engineering, you can't just go straight to flight when construction has finished. Ahead of the first flight of any EXØ-1 booster, I perform many component and integrated qualification tests. These include pressure testing, recovery deployment testing, rocket load and dynamics testing, and finally an all-up wet dress rehearsal where I take the rocket all the way through the launch countdown without actually releasing it to discover and diagnose any issues that popped up. Once all the issues have been resolved, I run flight profile simulations through several publicly available water rocket simulators. The best one that I've found is the Air Command Rocket Simulator, to get an apogee estimate and therefore a motor time estimate. On launch day, I bring the rocket out to the launch pad, pack the parachute, and pressurize in stages to reduce the work I need to do in the last few seconds before flight. I arm the recovery system, run final pressure checks, press record on all the cameras, and finally, liftoff. At full thrust, EXØ-1 clears the pad in about 1/10 of a second. It pushes out the full water load in about 1/4 of a second, dropping to just 1/3 of its liftoff mass. The rest of the ascent is spent coasting, with the rocket reaching apogee around 3.5 seconds into flight. EXØ-1 Block 1 caps out at an altitude of about 150 feet, Block 2 can reach 200 feet, Block 3 can reach 250 feet, and Block 3+ is capable of almost 400 feet. EXØ-1 Block 3+ has a payload capacity of over 500 grams to 200 feet, and Block 3 can bring the same to just under 150 feet. The rockets can fly with onboard cameras, airflow experiments, a multitude of sensors, and much more. Just after apogee, the V3 recovery system ejects the parachute and the rocket makes its descent back to the ground. Parachute sizes can range from 16 inches to almost 30 inches depending on weather conditions and desired touchdown speed, and once the rocket is back on the ground, the recovery system is disarmed. The launch pad's packed up and everything is brought back for post-flight analysis and review. EXØ-1 is my largest and most powerful rocket to date. It has flown over 60 flights, with more being completed every week, and Booster 2 is my most flown rocket ever, with over 50 flights under its belt in a span of about 2.5 years. This rocket is really a jack of all trades when it comes to water rocketry, having flown high-altitude flights, 2-stage flights, and payload-carrying flights or experimental flights. It's actively developing systems for more advanced rockets and just absolutely insane projects that I'm working on in the background, each of which will get their own versions of this video when they're done. In the meantime, I hope you've enjoyed learning a little bit more about what actually goes into these rockets, and I hope that you will all tune in again soon when I announce what I'll be working on this summer. It's going to be super exciting. Anyways, thank you for watching. Go build something cool.